Okay, you've either done that or you haven't. You've evaluated the square root of 169, and hopefully, well, what do you get from it? What is the square root of 169? 13. Yep, so it's just that. No tricks. That is equal to 13. The square root of 169 is equal to 13. Now, I want you to solve that. Kind of the same question, isn't it, really? So, solve x squared equals 169. So, x is equal to plus or minus 13. That's right. 13 is the right number, but it's plus or minus 13. Can I ask, just for an understanding question, why is the square root of 169 13, but the solution for x, where we're basically solving by square rooting both sides, why is the answer to x squared equal 169, x equals plus or minus 13? Okay, glad I asked the question. The difference is, on the left-hand side here, I'm asking you to evaluate the square root of 169. The square root of a number is always given as a positive number. The square root of 169 is 13. Square root of 25 is 5. It's not plus or minus 5, it's 5. Here, when I have a variable involved, I'm actually asking a different question. I'm actually asking what possible values satisfy the OG equation. So the OG equation is x squared equals 169. And the answer to that is, well, 13 fits that equation because 13 squared is 169. But minus 13 also fits the equation because minus 13 squared is also 169. So on the left-hand side, evaluate root 169. The answer is, and only is, 169. If I'm asking for solve for x, then what I'm actually literally doing is saying which possible values will give me that, will satisfy the original equation, which is why it's plus or minus 13. Does that make sense? It's really important that you get that, because if you don't, it makes the rest of the stuff kind of a little bit more difficult. So if I was spelling out the equation, this is all I'll say on it. I would say x squared equals 169. Therefore, x equals plus or minus the square root of 169, which is plus or minus 13. That's how I would do it. Okay, it's also in the quadratic equation why we say negative b plus or minus the square root of b squared minus 4ac. We don't just go negative b plus the square root of b squared minus 4ac, and then when we square root it, we put the plus or minus in. We've got to put the plus or minus in before, because the square root of a number is just a positive number, or 0 if it exists. Okay, all good with that? Why it's important is because the square root function is exactly what we are exploring today. And again, I'm trying to get a little bit faster each time, because it really is just, here is what it looks like, and then then how do we deal with transformations, and then let's do some problems. That's kind of what we're doing. So I'm going to start by having a little look at our old friend Desmos. And here's a little something that I prepared earlier. And this should look familiar to all. It is y is equal to x squared. It's your standard base parabola, quadratic. Okay, so it looks like that. And what we're going to do is we're going to flip the inputs and the outputs. And I'm going to do this on the whiteboard, so it won't be in the video. But if I flip the inputs and the outputs, if I had y equals x squared and flip the inputs and the outputs, so that means x's become y's and y's become x's, I'd have that. I'll just flip those around so that we've got left to right y on the other side. And then if I square root both sides, I would get the square root, the plus or minus square root of x, for the reasons I said before. You've got to go plus or minus when you've got variables involved there. We okay with that? So y is plus or minus root x. It would look like, hopefully this shouldn't be too surprising, like that. Yeah, kind of on its side. Because the inputs, or the domain, are now the outputs, the range of this red line, and the outputs, which is the range of the blue line, become the inputs, the domain of this red line. Okay, so we've flipped them around, and so we should get that. What I've done is I've kind of found an inverse of this. That is the inverse of that. Okay, so that is the inverse of that. Okay, now is this one-to-one, one-to-many, or many-to-one? If it's one-to-one, it means that if I look at any point on the x-axis, it will go up to a value on the line, and it won't go, and that'll only be true for that one pair. It won't be true for any other pair. Many-to-one would mean that if I went up to the line, like along the x-axis, and went up, I'll get to a point. And maybe if I go to another point like this and go up to the line, I'll get to the same point. That means many being more than one, many to the same coordinate for y. That's many-to-one. So quadratic is many-to-one. Is this many-to-one? Not really. But it is one-to-many. Yeah? E.g., if I look at the coordinate x, I'll go up to 2, and I'll also go down to -2. So for the one x coordinate, or the one input, I get 2 outputs. A one-to-many is a problem. Why? Not a function. What is it? Yeah. Remember, all functions are relations, but not all relations are functions. So a one-to-many relation, I've been tongue-twisted a bit because I've been trying to avoid the word relation. A one-to-many relation will not be a function here because it fails the vertical line test. For a function to be a function, it can have only a unique output for any input. Okay, so it kind of fails that test there. It doesn't quite work for the square root function. And what we really do for the square root function is we don't consider the plus or minus. We, in fact, and you can see that with the next one down, we've got y is equal to the square root of x, not the negative root of x, just the square root of x like so. This is now a properly formed function, and I'll just turn it on. It's just that green part. You can see it's exactly the same as that parabola on its side, but it's just that green part there. So it's only the positive. Let me get rid of the rest of the details so you can see it now. And that is the base graph of a square root function. It starts off at 0, 0. It feels like it might have some sort of horizontal asymptote up there somewhere, but it doesn't. It just grows. As it goes on, it grows a bit more slowly as it goes, but nevertheless, it is just growing that way, like so. So that is y is equal to the square root of x. Okay, so a couple of notes to write. There we go, bottom left-hand corner. So write some notes. The square root function. The base function is y equals root x, and it just goes up like I've gone there from 0, 0. Nice and simple. No asymptotes. It just starts at 0, 0 and heads right. Heads for its freedom to the right. Where things get interesting with the square root function, and I use the word interesting advisedly, is that the domain and the range needs to be considered carefully. The domain and range of the base square root function is much more restricted than we've been having had to deal with previously. And if you look at the graph, you should probably be able to work out the domain for yourself. What's that, sorry? I won't wait, but yeah, you go. Who wants to be brave and say what the domain is for the base function? Yep, 0 to infinity. I'll use the real number notation. You could do that. That's all you need to write. I'll do in blue the other notations that are okay. Square bracket, infinity, round bracket. Or you could go x is real, x greater than or equal to 0. The one thing you can't have basically is you can't just write the domain is x greater than or equal to 0. You can't just write that by itself. You have to have x. I'll just zoom up so you can see that. Sorry, guys, it's probably easier. You can't have just x greater than or equal to 0. So it's one of those two. You have to have x belongs to the real set or at least have the interval notation there. All of those are legit. What about the range? Someone else want to be brave enough to go for the range? Okay. Same as x. Beautiful answer. I'm just going to write the one notation in. You may write whatever notation you want to. It's important that you are aware of this notation, though. So remember that little u stands for union. It means combine these two sets together. Oh, actually, that's not very nice, Richard. I forgot my little pluses. There we go. All positive real numbers plus the number 0 is what that means. The set of real positive numbers, that's to the left of the union sign, union with the set of numbers which is just 0. Okay, we cut it in half so that it was not one to many. That's why we did it. When I say cut it in half, we didn't really, because y equals root x will only give us the positive square root. So that's fine. We cut it in half, though, the relation y equals plus or minus root x to give us that function. But what are we left with? Are we left with a one-to-one function? In other words, if I go along to anywhere on the x-axis for the specified domain, will I get only one value in the range and no other value of x goes to that number? That's what one-to-one means. If I go along the x-axis, I'll get a corresponding y value, and is that the only time that y value is hit, is what I'm saying? Or is it many to one, which means I'll go along the x-axis, I'll go up, and I'll get a corresponding y value, and somewhere else I'll go along to the x-axis and go up, and I'll get the same y value. That would be many to one. Yeah, what I'm saying, one-to-one. It's one-to-one. So this is an example of a one-to-one function. Okay, all good with that? Questions? Right, let's have a look at the effect of transformations, and then we'll be more or less good to go. I'll do one example, but it should be fairly quick to get you into work after that. So back to Desmos. You can see that I've got the function in this format here for all transformations. Y equals a root b outside of x minus h plus k. Just a reminder, I'm sort of adjusting things as I go along from last year. But if I had, for example, just doing this just for the video, I'm just saying I'm doing this on the board. If I had the y equals the square root, and if I'm going to make it easier for myself, 2x minus 4, if there is a coefficient of x here, it can always be isolated from inside the brackets, like that. Can always be isolated out. And having it in this format means that I can basically just use the dilation, reflection, translation model for both x and y. So if I left it like this and I had to list the transformations, I would have to say translated 4 units to the right and then dilated by a factor of a half in the direction of the x-axis. For this one here, and it would give me exactly the same graph. I could say dilated by a factor of a half in the direction of the x-axis and translated by 2 units to the right. So that's kind of why we do it, because it just gives us a constancy when it comes to describing our transformations. There's other benefits too, but that will do for now. Okay, so hopefully these will do what you would expect. If I increase A, oh, you know what would be useful? If I actually turned on the transformations there. If I increase A, it is now stretching away from the x-axis because it's a dilation in the direction of the y-axis. So we're getting a stretching away from the x-axis, a stretching up. And if I go between 1 and 0, it's shrinking towards the x-axis. It's growing a lot more slowly, and so it is dilated by a factor of a half in this case in the direction of the y-axis. If I go to A equals 0, it's a very boring graph. You don't have to pay attention, I guess, if you know it all, but you just go and do something else. Or if it's a question, raise your hand and ask, and then I'll get clarity. But what I don't like is people just having a bit of a chatsy when I'm trying to teach the whole class. It's just courtesy, right? If I go to -1, it's reflected about the x-axis, like so. Okay, so it's a vertical reflection because it's reflected about the x-axis and dilates towards away from or towards the x-axis in the direction of the y-axis. Okay, all good with that? I don't want to dwell on it too much because I think it's stuff that you've seen a bunch of times and I don't want to do overkill. I'll bring it back to 1 just so that we can focus on things one at a time. This does a dilation this way. Kind of looks the same, doesn't it? But what's really happening is that as I'm increasing B, it is being pulled towards the x-axis, the y-axis. So it's a dilation in the direction of the y-axis. But it does kind of feel like it's doing the same sort of thing. But it's only because of the shape of the graph. If you kind of focus on this little area here, you can see this is starting to peel towards the y-axis, sorry. That's what's doing. It's peeling towards it. Okay, and similarly, if I do that, it's negative, it's reflecting that way instead. So we've got a complete swap. Can I move on? Yeah, cool. H does what you'd think it would do. If H is positive, i.e. it's X minus something, it's going to crawl away to the right. If X is negative, i.e. it's X plus something, it's going to crawl to the left. And if K is positive, up it goes. If K is negative, down it goes. Ultimately, what you're doing really is when it comes to sketching it, I'm going to do an example in a second, you're having a look at what happens to that, to where the end point is. So if I go H equals 2 and K equals negative 3, then the coordinates of the endpoint is now 2, negative 3. So you start there, you draw your graph, and as usual, you then use you use the facts that you've been given, like the dilation factor and all that kind of stuff, to work out where the x-intercept is, if it exists, because it might not, and where the y-intercept is, if it exists, because it might not, but then again, it might. So you just work it out as you go along. Okay, any questions on that before I move on to a worked example? Speak now or forever hold your peace. Okay, last thing then. What you'll notice here is if I make B equal to 3, we've got this, dilation effect happening in the direction of the x-axis. But have a look at this graph here. This is exactly the same, right? This is exactly the same. So what I've done is I've taken out a common factor of b, yeah? So I'll just use a specific number here so you can see it. Again, for the video, I'm using the whiteboard. So if I had y is equal to the square root of 2x minus 2, I could break that down to the square root of 2 multiplied by the square root of x minus 2. So what we can do is we can isolate the value of b and square root it effectively and take it out, and now we can say that the graph is a dilation in the direction of the y-axis by a factor of root 2. I'll say that again. In this equation here, y equals root 2x minus 2, I'm saying it's a factor of a half in the direction of the x-axis because it's inside the square root function, so that's a dilation there. But I'm saying it's the same as root 2 multiplied by root x minus 2, so it's the same as a dilation of root 2 in the direction of the y-axis. So the dilation effect is exactly the same. So have a look as I do this. As I stretch these two, you can see the orange and the purple graph are exactly the same. Watch it, keep watching it, keep watching it. Still the same. What's happened here? It reflected, but it also changed color. Why is that? What am I doing here? Let's make b just nice and simple, minus 1. The orange has disappeared. Why would that be? Yeah. If I take out the common factor of b, when b is negative, then I'm taking out a square root of a negative number, and that'll cause my graph to effectively disappear. Whereas if it's inside the square root, that negative 1, if I just go backwards and expand it, that negative 1 is captured within the bx minus bh effectively. So although it can exist here, when I take it out, it kind of it makes it impossible to graph in that form. Okay, so you've got to be careful. So more or less, feel free to take out the square root of b when it's take out the factor of b and make it a square root of b when it's positive. I mean, if you had something like y equals the total square root of 4 outside of x minus 1, it's nice and easy to go, well, the square root of 4 is 2, so it's 2 root x minus 1. It makes sense to do it in that regard. But otherwise, and then you've got rid of the horizontal dilation completely. There's nothing there. You can just deal with it with a vertical one. But in some circumstances, it may cause you to for it not to work. So you just got to be careful. So I'll make b 4, and there we go. We've got b equals that will be 2 here and 4 here. So same difference. Okay, cool. Any questions before I do an example? Then I'll let you get to work. Awesome. Away we go. Okay, so simple example. Oh, sorry, before I do the example, here's some notes that you can take down. So transform function looks like y equals a, the square root of b outside of x minus h plus k. This can be, the b can always be factorized out unless b is less than 0. So effectively, you just need to learn, well, that's probably a bit too broad, but you just need to learn y equals a outside of root x minus h plus k, with the exception that if b is less than 0, i.e. if b is less than 0, then you probably need to keep it there. But the rest of it's true regardless. You've got the end point being h comma k, and then the graph goes on like I've drawn there. There's no real context for the dilation factor in that diagram, but nevertheless, there you go. Okay, let's do the worked example. So it says sketch y equals negative 2 root x minus 3 plus 1. So in your brain, you should be going, I can see it's reflected, so it's going to be going downways instead of upways, because it's a reflection about the x-axis. It's going to be reflected. It's going to go across 3 units and up 1 unit. That's going to be my new endpoint. So you're just sort of thinking these things, and then you're formally writing it down to make sense. So number 1, the endpoint is equal to 3, 1. Yeah? H, K. Number 2, noting that's a reflection, therefore it looks like that. It's worth just writing it down, because then when you're looking at the facts and looking at your graph, you tend to have to keep less in your head. Number 3 is the y-intercept. Now, you can use common sense for this. If I've gone across 3 units and up 1 unit, my base graph is going to be, if I'm just going to flick over for a second, my base graph is going to be up here somewhere, right? So there's definitely not going to be a y-intercept because I've moved away. If I moved backwards, there will be a y-intercept. But because I've moved forwards in the graph, there will be no y-intercept. You can use the same logic for up and down as well. Okay, so y-intercept, none, done. Number 4, the x-intercept is where we need to put a bit of work into it. The x-intercept is solved just like we do every single other function. We let y equal 0 and solve. So when we let y equal 0, that makes 0 equal to negative 2 root x minus 3 plus 1, like so. And now I'm going to subtract 1 from both sides. You can do this faster if you need to, but I'll just take my time. Minus 1 equals minus 2 outside of x minus 3. Then I'm going to divide negative 2 for both sides and get root x minus 3 on one side and 1/2 on the other. I've just swapped sides at the same time. Now, it's at this point, guys, that if you've got a negative number on the other side of the equal sign, oh, no, it doesn't matter because we're squaring it anyway. No, it's all good. Ignore what I was about to say. Okay, the next thing is to square both sides. So I'm going to get x minus 3 on the left, and I'm going to get 1/4 on the right. The next thing I'm going to do is add 3 to both sides, and I get x equal to 3 and 1/4 will do. 3.25 if you're keen. But I'm not. I'm quite happy with 3 1/4 and 0. So what does that give us? It gives us a graph where the new starting point is 3, 1. So I can put that in first. So 1, 2, 3, 1, something like that. It's going to have this shape, so I'm going to do that. And then this point here is 3 1/4, 0, like so. I'll zoom up in a tick just so you can sort of see that. But that's basically it. And I should remember the niceties. I should practice what I preach, and that is you should label your axes, put arrows on the end of your axes and all that kind of thing. Yours? Yes, thank you. I 100% should have done that. Thanks, Sonny. Good call. That's 3, 1. Okay, I'm going to zoom up on that so you can sort of see it a little bit more clearly. I squished it in a bit.